The first item was sketching the events when an AP, an action potential, reaches the synaptic terminal and opens voltage-gated calcium channels. So this person has shown an action potential moving down an axon and showing secondary active transporters, potassium leak channels, just the background for all of it. Here is at the front end, we have a voltage-gated sodium channel open, two of them open, sodium coming in, and so we're going from threshold minus 45 to plus 30. Then behind it, the voltage-gated potassium channels open, allowing potassium back out, and the voltage-gated sodium channels are being inactivated, and further back, everything is reset, and we're just back to minus 70 back here somewhere. The positive charge is opening voltage-gated calcium channels here. Calcium comes in, binds to a calcium binding protein. It's called synaptotagmin, and that binds to proteins on the membrane, spans them with the vesicle, and causes vesicle fusion and release of neurotransmitter. Most people combined B and C, events from release of neurotransmitter. And so here's the neurotransmitter, and then when we have an ionotropic ion channel, the receptor is, an ionotropic receptor, the receptor is a channel, and so the sodium is going through that receptor. It is faster, but there's no amplification. If it's a metabotropic receptor, then it's doing something like activating a G protein. Many are, but there are other types of metabotropic receptors. And the G protein might be causing adenylate cyclase to make cyclic AMP, which then binds to a sodium channel and allows sodium in. And of course, you can use different second messengers and different ions coming in. It is a little slower because you have to wait for these additional steps, but you get amplification. Each neurotransmitter binding event gets you multiple, maybe 10 or more cyclic AMPs that wind up bound to a channel. Most people skipped this one, just a reminder about different regions of a neuron. And then in this case, I wanted EPSPs and IPSPs showing an IPSP excitatory with sodium. So here sodium is coming in. We have a metabotropic receptor is what's being shown, a second messenger that then binds to sodium channel, allows sodium in, it's more positive, and so that would be excitatory. Here's inhibitory. We have the same inputs from receptor, second messenger, but in this case it's binding to a potassium channel, allowing potassium out. That's positive charge leaving the cell gets more negative, it is inhibitory. And then an excitatory synapse, again, second messenger. In this case, it is blocking a potassium channel. That means we have less potassium leaving, and so the cell gets more positive, exactly. So it's excitatory because we've blocked a potassium channel. Here's another example showing an inhibitory synapse where we're opening a potassium channel. Second messenger, cyclic AMP, opening a potassium channel. It's making it more negative as potassium leaves. Here is an excitatory synapse in which we're blocking a potassium channel, and so the cell becomes more positive. And here's an excitatory synapse in which we're opening a sodium channel, and this person is showing either positive charge moving toward the axon hillock or negative charge. All of it's summing here with some dispersion, of course. And then the question is, does the sum of all the positives and negatives get us to minus 45 and a threshold or not at the spike initiating region, SIR? This one I wanted to have people think about because in a typical sensory neuron, it is unipolar. In other words, it has only one projection here, and that projection then goes in two directions. These are functioning like dendrites, and that's where the inputs are coming in. The action potential is going along this whole length out to the axon terminals, where we're getting neurotransmitter release. And so the action potential actually starts in here. The spike initiating region in these is here. It's really one giant axon, but this part out here is actually functioning as dendrites. Synaptic tagging, I saw some great sketches. Some were very complex. This one I liked because it's pretty straightforward to follow. We have binding here. We've got second messenger that opens a calcium channel. What they're not showing is that that same second messenger might also open sodium channels. So they're not showing the action potential, which makes this whole thing simpler. So this shows only the calcium entry. That calcium then binds to a kinase, which puts a phosphate on a protein that will cause, or that may cause translation of messenger RNA at ribosomes that are out here in, very near the dendritic spine. And so I gave two versions of it. One in which this protein winds up causing more of our receptors to be made and other proteins that are necessary to maybe increase the size of a synapse, and so you strengthen the synapse. You get more receptors and therefore more response to exactly the same neurotransmitter released later. Then this person added in the retrograde transport, in other words, backwards transport. So down here at the cell, if there's an action potential, that action potential can do a number of things. But all of the hypotheses involve some backward signal, often some protein. And I just had us take a protein and phosphorylate it and then have it be packaged to transport back along microtubules. But there's multiple mechanisms proposed, and the most recent papers I've seen from about 2018-19 don't have any single mechanism, and probably there are multiple mechanisms for this. Anyway, we need some signal, in this case a phosphorylated protein, and if we set our conditions such that we need both the protein that's phosphorylated because of this calcium signal here at the dendritic spine, and only if there was an AP that came from this do we get the signal back. This protein is sent back to all of the dendritic spines, but the only one where it makes a difference is here where we also have this protein. So only where we have the two proteins together are we going to get the messenger RNA translated into a protein that strengthens our synapse. So that's a way to strengthen only the synapse that actually caused or was associated with the action potential. Here's another version that just showed synaptic tagging of the dendritic spine that was stimulated. So this one has our action potential, or potential for an action potential here is the positive charge heading toward the spike initiating region, but it also opens voltage-gated calcium channels, calcium binding to calcium binding protein, which activates a kinase, and it's putting a phosphate on these two proteins. These two proteins then interact in some way with a messenger RNA, and they wind up helping that messenger RNA get to a ribosome, move through the ribosome, we get a new protein, here's more receptor, and we strengthen our synapse. This one does not include the retrograde signal coming back from the nucleus that might be also required for translation. So it depends on whether our synaptic tagging is going to mark this just because it got an action potential, or only if after it received neurotransmitter an action potential occurred in that neuron and sent a signal back specifically to strengthen this signal. Here's another version of that that I just showed.